Hey, Cal 2 students. Today we are going to be looking at area one last time. Last time we used Riemann sums to do this, and there's practical value for us knowing how to do that. There's also practical value and application for us being able to compute the area bounded by two curves using a formula. So that's what we're going to look at today. First of all, realize that our strategy for computing the area bounded by two curves was essentially to take rectangles of width delta x and fill up the bounded area with those rectangles, and then add the areas of the rectangles. And then we let the limit, we compute the limit as delta x goes to 0 to get the exact area. Here's how it looks. Here's the setup. We have two curves, or two functions, f of x and g of x, and they're continuous. The graphs have no breaks or interruptions. And we assume that f of x is greater than or equal to g of x. In other words, in the xy plane, the graph of f of x lies above the graph of g of x. And we're computing the area bounded by the two graphs from x equal a to x equal b on the x-axis. So here's what we did. We took the interval from x equal a to x equal b, and we partitioned it into n subintervals of equal length, delta x. And if you remember, delta x equals the length of the interval from a to b divided by the number of subintervals n. And over each of these subintervals, we constructed a rectangle of width delta x such that the top intersected the graph of f of x at the point x sub I, f of x sub I, and the bottom intersected the graph of g of x at the point x sub I, g of x sub I. And we computed the areas of the rectangles. The area of the ith rectangle is the height, which is the difference of the y coordinates, times the width, delta x, and then to get the total area bounded between the graph of f of x and g of x, we added up the areas of all of the rectangles. And that gave us an approximation. To get the exact area, we let delta x go to 0. And what happened when we did that? Magic. The summation sign turned into an integral sign. The x sub i's turned into x's. And the delta x turned into dx. This becomes a definite integral. And how do we know what the end points are? The foolproof criterion is this: the endpoints of the interval that we partition into subintervals will be the limits of the definite integral. So in this case, A will be the lower limit, B will be the upper limit. Now, let's take what we just derived and make this the general rule. So this is what we've just established. Given continuous functions f of x and g of x, with f of x greater than or equal to g of x, the area bounded by the graphs of f of x and g of x over the interval AB on the x-axis is this: the integral from x equal a to x equal b of f of x minus g of x dx. And we will be computing area this way. The fact of the matter is that there are a number of applications in mathematics, especially in statistics, where we need to be able to compute the area bounded by the graphs of two functions. And when we use this formula, we'll be calling it the f minus g method. Okay, here's a good exercise for us to work. Compute the area bounded by the graphs of f of x equals sine x and g of x equal cosine of x over the interval from 0 to 2 pi on the x-axis. And sine and cosine are continuous functions, so this looks good. Oh, let's see. One more thing. Yep, we're going to use the f minus g method. So we take the integral of f of x minus g of x from a to b. The antiderivative, negative cosine of x plus sine of x, is that right? Let's say. Antiderivative. Antiderivative, negative cosine of x, negative sine of x, yep. From x equals 0 to 2 pi. Plug in the upper limit, plug in the lower limit. Whoops, I got a negative sign there. Okay. The cosine of 2 pi is 1, so we have minus 1. The sine of 2 pi is 0. The cosine of 0 is 1, and we have a minus there. Sine of 0 is 0. So we have negative 1 minus a negative 1. 0? I find it hard to believe that over the interval from 0 to 2 pi, the graphs of these two functions bound absolutely no area. I don't know, maybe it's right, but somehow I don't think so. The graphs of sine and cosine have to, there's some area between those graphs. How on earth did we get 0? Well, let's just make sure. Let's draw a picture of what's going on. Okay, I got my graph of sine of x up here. I got my f of x. Now let me draw the graph of cosine of x. Okay, here's my graph of g of x. G of x equals cosine of x. And the graphs of these functions definitely do bound positive area, a non-zero amount of area, between x equals 0 and x equals pi over 2. Let's look at all of this area that's bound by the graphs of the two functions. Whoa. My goodness. Look at all of this area. Now, how the heck did we get 0 for an answer? The formula says that the integral from a to b of continuous functions f of x and g of x, the area bounded between those functions, is the integral from a to b of f of x minus g of x, where f of x is the f of x is the larger function and g of x is the smaller function. The f minus g formula only holds as long as f of x is greater than or equal to g of x. Look at this. F of x equals sine of x. Well, right here, sine of x is less than cosine of x. Our f of x is less than g of x from 0 to, where do these graphs intersect? Pi over 4. So from 0 to pi over 4, cosine is the greater function at pi over 4. And then from pi over 4 all the way to here, sine of x is the greater function. And I guess this will be 5 pi over 4. At 5 pi over 4, the graphs crisscross again. And from x equal pi over 4 to x equal 2 pi, cosine again is the greater function and sine is the smaller function. Okay. That's what our problem was. If we had drawn a graph of sine of x and cosine of x before we used the formula, we would have seen that sine of x is not the greater function throughout the interval from 0 to 2 pi. And what have I been saying in class all along? Whenever we do an area function, our first step always, always, always is to sketch a graph of the bounded region. Graph the functions that bound the region. We didn't do that. And even if we use the F minus G method, we have to graph the two functions. We absolutely have to graph the two functions. Whenever we do an area problem, no matter which method we use, we have to use the F minus, we have to graph the functions first. Now let's do this thing again the way we should have done it from the start. Here's our exercise. Compute the area bounded by the graphs of f of x equals sine x and g of x equal cosine of x. From x equals 0 to x equal 2 pi. And what's our first step in an area problem? Always graph the bounded region. Here's y equals sine x. And here's cosine of x. Now let's make some observations. We start off with cosine of x being the greater function. From x equals 0 to x equal pi over 4, cosine is the greater function. Then between pi over 4 and 5 pi over 4, sine and cosine flip-flop. Sine is the greater function. And then starting at 5 pi over 4, cosine becomes greater again. So how are we going to do this? We're going to have to break the integral up into 3 different parts. whoops. This is the area that we want, from x equals 0 to x equal 2 pi. And that's equal to the area from x equals 0 to x equal pi over 4, plus the area from x equal pi over 4 to x equal 5 pi over 4, plus the area from x equal 5 pi over 4 to x equal 2 pi. From x equals 0 to x equal pi over 4, cosine is the greater function. And then from x equal pi over 4 to x equal 5 pi over 4, sine is the greater function. And then from x equal 5 pi over 4 to x equal 2 pi, cosine again is the greater function. So what do we get? Sine of x and antiderivative of sine is negative cosine, but there's a negative sign here, so integral of, or rather we get sine of x plus cosine of x evaluated from 0 to pi over 4. And antiderivative of sine of x is negative cosine of x. Antiderivative of negative cosine of x is negative sine of x. From, what is that, pi over 4 to 5 pi over 4. And again, antiderivative of cosine is sine of x. Antiderivative of sine of x is negative cosine, but we have a negative sign out front. So we have cosine of x from 5 pi over 4 to 2 pi. And this gives us sine of pi over 4 plus cosine pi over 4 minus sine of 0 plus cosine of 0 Okay, next frame. Negative cosine of 5 pi over 4 minus sine 5 pi over 4 minus negative cosine of pi over 4 minus sine of pi over 4 plus sine of 2 pi plus cosine of 2 pi minus sine of 5 pi over sine of 5 pi over 4 cosine 5 pi over 4 And let's see what this turns out to be. Square root of 2 over 2, square root of 2 over 2, minus 0 plus 1, plus cosine of 5 pi over 4 is negative square root of 2 over 2, but we have a negative sign out in front. Sine of 5 pi over 4 is negative square root of 2, but we have a negative sign out front. Cosine of pi over 4, square root of 2 over 2. Sine of pi over 4, square root of 2 over 2. And then finally, sine of 2 pi is 0. Cosine of 2 pi is 1. Minus sine of 5 pi over 4. Sine of 5 pi over 4 is negative square root of 2 over 2. And cosine of 5 pi over 4, negative square root of 2 over 2. Okay. I have a minus 1 here and a plus 1 here. They are gone. And let's see. I have minus and minus, that makes plus. And I have minus and minus, that makes plus again. So it looks like all of the terms that have square root of 2 over 2 are positive. Positive, 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 positive. And we have 1, 2, 3, 4, 5, 6, 7, 8 of them. Area is 4 square root of 2, which is a heck of a lot better than 0. The big lesson here is even if we use the f minus g method, we have to graph the functions first. Now let's get down to some better exercises. Compute the area bounded by the graphs of f of x equal x to the 1/3, g of x equal x cubed, and they don't tell us between x equal this and x equal that. So the presumption is these two graphs determine the bounded region by their points of intersection. And I'll tell you something about x to a power. Essentially, x to the power of any number. There are 3 points that we want to check. X equal -1, x equal 0, x equal 1. X to any non-negative power is going to go through the points 0, 0, and 1, 1. X to the power of an odd function, I call this odd because it's a cube root, is going to go through the point -1, -1. This is an odd function, it's x cubed. It's going to go through the point -1, -1. Whenever we have x to a power, think 3 points. X equal -1, x equal 0, x equal 1, plot those points. X cubed, I think we know what that looks like. X to the 1/3, if we take a number between 0 and 1, and we compute the cube root, we get something larger than the original. For example, let's take the number 1/8. If we compute the cube root of 1/8, we get 1/2, which is larger than the original. That turns out to be true of all the numbers from 0 to 1. The cube root is larger than the number itself. And what that means is, if we look at the graph y equals x, the graph of y equal cube root of x is going to be greater. The graph of y equal cube root of x is going to lie above the graph of y equal x, because between 0 and 1, the cube root of a number is greater than the original number itself. So here we have y equal x cubed. Here we have y equals x to the 1/3. And to the left of the y-axis, these two graphs flip-flop. This is now the graph of y equals x to the 1/3. And this is the graph of y equals x cubed. So we're in the situation again where no one function is larger than the other throughout the entire interval. Let's write down what we've established. Between x equal -1 and x equals 0, x cubed is the larger function. Between x equals 0 and x equal 1, x to the 1/3 is the larger function. From x equal -1 to 0, x cubed is the larger function. So we integrate the larger minus the smaller. And then at 0, the graphs flip-flop. And from x equals 0 to x equal 1, x to the 1/3 is the larger function. Whoops. Okay, time to integrate this son of a gun. And maybe I'll get there. Okay, plug in the upper and lower limits. -1 to the 4/3. Now let me just step back and make sure I've written exactly what I should have written. I think I did that correctly. Negative 1 to the fourth is 1 over 4. The cube root of negative 1 is negative 1 raised to the fourth is 1. So this is 1 times negative 3/4. 1 to the 4/3 is 1. 1 to the fourth is 1. Zero minus a half is 0 minus a negative half is plus 1/2. Plus 1/2. Okay. So we get a half plus a half is 1. With some of the weird results we get, I'm kind of surprised we got a whole number. Well, that's the way it works sometimes. Graph the area of the region bounded by the graphs of f of x equal x squared and g of x equal x cubed. Okay, first thing we do, graph the region. And again, our functions are x raised to a power, x raised to a power, and they don't give us find the area of the region bounded by the graphs of f of x and g of x between x equal this and x equal that. So the presumption is that the graphs by their intersection determine or define completely the bounded region. And here's what I think. Since we're graphing x to a power and x to a power, we need to take those three special values of x equal negative 1, x equal 0, x equal positive 1, and plot the points of the graphs for those points in particular. Those are always very special points in graphing x to a power. Okay? X squared. When we plug in 0, we get 0. So this is a point on the graph. 1 squared is 1. That's another point on the graph. And negative 1 squared is positive 1. So this is what our graph of x squared is going to look like between negative 1 and positive 1. Now let's do x cubed. If we take 0 and cube it, we get 0. So this is a common point on the graph. If we take 1 and cube it, we get 1. If we take negative 1 and cube it, we get negative 1. Now, is the graph of x cubed below x squared or above x squared? And think about this. If we take a number between 0 and 1 and square it, what happens? Let's say we take 1/2 and we square it. we get a quarter. So we get a number that's smaller than the original. If we take 1/2 and square it, we get a quarter. What happens if we take 1/2 and we cube it? We get 1/8. That tells us something. For x values between 0 and 1, x cubed is smaller than x squared. So the graph of x cubed is going to lie below the graph of x squared. The region bounded by the graphs of x squared and x cubed lies completely between x equals 0 and x equal 1. This is the bounded region completely. This is the entire bounded region. And throughout the bounded region, x squared is greater than or equal to y cubed. Oops, I did not mean to do that. Larger function minus smaller function. This is going to be 4/12. That'll be 3/12. These exercises are getting easier, aren't they? Absolutely. Here's an exercise that we should see. Compute the area bounded by the graphs of y equals x squared plus 1. I'm sorry, x equals y squared plus 1, and x equals 2y squared minus 3. Both of these are quadratics in y. The coefficients of y are positive. So these are parabolas that open up in the positive x direction. They're both going to look like this. What else do we know? Maybe we should think about the vertex. And we were concerned about this because the first step is always to graph the region. Now, we know that these are both parabolas. They both open to the right or in the positive x direction. What's the vertex? Well, let's see. The derivative of x as a function of y is going to be 2y in this case. And if we set that to 0 to find the critical number, we'll get the y coordinate that gives us the minimum. Critical number when y is 0, x equals y squared plus 1. Okay, we know something about this. Vertex, y equals 0, x equals 1. Let's do the same thing with this. compute the derivative of this with respect to x, and we get 4y. And if we set it to 0, we get the critical number. Y equals 0 is a critical number again. Our vertex is going to be at y equals 0. When y is 0, x equals 2y squared minus 3, which equals minus 3. So the vertex is y equals 0, x equal negative 3. Let's write that down. We notice something else here. It doesn't say compute the area bounded by the graphs between x equal this and x equal that, or between y equal this and y equal that. So again, the presumption is that these two graphs, by the way they intersect, completely define the region whose area that we want to compute. So I guess we better figure out where they intersect, right? Okay. Where the graphs intersect, the x coordinates will be the same, the y coordinates will be the same. So here, let's set the x coordinates equal. Find points of intersection. Set x coordinates equal. And we'll see what that forces y to be. Here's one x coordinate, y squared plus 1. Here's another x coordinate, 2y squared minus 3. We're going to set these equal to each other. X coordinate, we're going to solve for y. And I'll subtract y from both sides. I'll subtract 1 from both sides. Okay, so these things intersect when y equals negative 2 and when y equals 2. When y equals negative 2, what is x? Negative 2 squared is 4 plus 1 is 5. So 5 is the x coordinate of one point of intersection. And let's see, when y equals positive 2, y squared is 4 plus 1 is 5. Okay. When y is 2, x again is 5. These are the points of intersection. Now we'll plot the region, and from here on out, this exercise is going to be so easy that even I can do it. I'll graph the two vertices, 1, 0, and negative 3, 0. Those are the vertices, and the points where they intersect, x equal 5, and y is plus or minus 2. Okay. So where is x equal 5 here? And which graph is this? This is x equal y squared plus 1. Okay, now this other guy, its vertex is way the heck back here. I guess that doesn't look too bad. Whoops. X equals a function of y. X equals 2y squared minus 3. If we were to integrate in terms of x, the greater function would be on top, the lesser function would be on the bottom. We have several problems here. Here's the greater function, here's the lesser function. But then here's another greater function, another lesser function. And then over here, here's the greater, here's the lesser. We'd have to rewrite the definitions of these functions, and we'd have to integrate at least 3 times. We'd have to integrate once to get the area from here to here, and the area from here to here. And then we'd have to integrate a 3rd time to get the area from here to here. In the lingo of one of my esteemed colleagues who has since retired, that ain't going to work. It will work, but it won't work well. It will be such a pain that we don't want to do it. But if we integrate with respect to y, we just integrate the greater function minus the lesser. And if we integrate with respect to y, in other words, x being a function of y, the greater function is the one that lies farthest to the right. The greater function is the rightmost function. So this graph right here is the graph of the larger function. And this graph is the graph of the lesser function. This graph, at all points in the bounded interval, lies to the left of this graph. So the larger function is x equals y squared plus 1. The lesser function is x equal 2y squared minus 3. We only have to integrate once. And let's see. Y goes from -2 to 2. And the greater function, and maybe I should explain this. If we're integrating with respect to y, we're going to be drawing our rectangles horizontally. And so this is the interval that will be spanned by the rectangles, and it will go from -2, y equal -2 to y equal +2. And we'll have the larger function, y squared plus 1, minus the lesser function, 2y squared minus 3, dy y squared minus 2y squared is -y squared. 1 minus a -3 is +4. Did I do it right? Negative 2 cubed over 3, 4 times negative 2. I think I did. We have negative 8 cubed. I'm sorry, negative 8 over 3 plus 8 minus, this is negative 8 over 3, minus that is 8 over 3. Whoops. Minus 8. Negative 8 thirds. Negative 8 thirds is negative 16 thirds. And 8 minus a negative 8 is 16. This 16 thirds is the same as 48 thirds minus 16 thirds. 32 thirds. That's my area.